So in the last lecture, we looked at how to solve logarithmic equations that have a single logarithm in them. In this lecture, we're going to take it a step further and look at how we can solve equations that have multiple logarithms. And the process is going to rely heavily on these three properties of logarithms. Like I said in the last lecture, I don't want to drill too deeply into the specifics of these properties, where they come from, how they work. Our focus is on solving equations, so I really want to look at these just as tools that we can use as part of that process. All right, and what I want you to kind of notice is that all three of these on the right-hand side have a single logarithm with nothing out in front, no numbers out in front, no coefficients like this one has. Right. That's how we're going to handle the multiple logarithm case. We're going to use these properties to combine all of the logarithms into one. And then once we've simplified this to the point where it's a single logarithm equals a number, okay, now it's going to proceed exactly like the ones we did in the previous lecture. All right, so let's look at some examples. Take this one here, right? Multiple logarithms, right? And I need to simplify this. All right, well, the first thing I'm going to do is I see this log base 2 of 4 over here. There's no variables in there, yeah? And more important, I actually know what that is. That's going to be, not only is it going to be a number, it's going to be a nice number, right? That's saying 2 to what power is 4? Well, 2 squared is 4, right? So I can simplify this to 2. And it equals 5. I'm going to kind of leave everything else alone here, just doing one thing at a time. Right, now remember what I said earlier. Right, our goal here is to get this so that it looks like a logarithm with some expression in here equals a number. So I know I got to get all the numbers over on one side. So I'm going to go ahead and subtract 2. And this becomes 3 log 2 x minus 1 equals 3. All right, it's starting to look like what I want, but we're not there yet. You can't apply the definition to this thing the way it's written. And the problem is this 3 over here on the right-hand side. Our definition says the log base a of x equals y is equivalent to a to the y equals x. Well, it doesn't say anything about there being a number out in front, like we've got here. Right? But fortunately, I can fix this pretty easily, right? I can just divide both sides by 3, and we get the log base 2 of x minus 1 equals 1, and now it has this form. All right, now I'm going to use the definition of a logarithm to convert this to an exponential version. To do that, the base stays the same, so the base of the logarithm is 2. The base of the exponential version will be 2. And the 1 and the x minus 1 switch sides. So the 1 comes over here and becomes an exponent. The x minus 1 goes over here. And there you go. We're there, right? Let's add 1 to both sides, and we get x equals 3. And that's my possible answer. All right, there's one more step you have to do with these logarithmic equations, and I really want to emphasize this. We need to check our answer, right? We need to check our answer, and I really want to emphasize that this is not an optional step when you're doing logarithmic equations, solving logarithmic equations. I know we're doing all sorts of other linear polynomial equations, whatever. There's a strong tendency to skip that step. You know, I'll admit I do that as well. You cannot do it here. There are going to be times when you do absolutely everything correctly, and one or more of the answers that you get actually don't work, right? And we'll see an example of that in a minute here. But what you really need to do, you don't need to completely simplify or completely test your answer. What you really need to do is go back, put it into the original. I'm going to do that over here. Right, this will be 3 log base 2, 3 minus 1, plus the log base 2 of 4 equals 5. Right, so if we do this, what happens here? This 3 minus 1 becomes 2. And that's really the part for testing purposes that I cared about. You'll see again in examples here in a minute, sometimes that expression will be negative. And that's not okay, right? Because you can't take the logarithm of a negative number. So that's really the key thing that we're looking for. When we do this substitution for testing, if one or more of the expressions we're taking the logarithm of becomes negative, then we have to throw away that answer. Right? But that didn't happen here. Right? 3 minus 1 is positive 2. So that's a perfectly good answer, and that is our final result. All right, so how about this one here? Little busier, right? We have variables in both logarithms. Okay, fine. So let's see how we can simplify this. All right, well, remember my method here. I need to turn this into a single logarithm equals a number. And I'm feeling good about the right-hand side because I already have just a number over there. So what I need to do now is combine these logarithms together. And I can do that because they have the same base. All right, remember the rule I'm going to apply here is the one that says the difference of two logarithms, let me put a base in there, is equal to their ratio. All right, so that's what I'm going to do here. I'm going to make this the log base 4 of x squared minus 9 over x plus 3 equals 3. Now I've got it in that form that I need it to be in, right? But I'm actually seeing, because I'm looking ahead a little bit, I can actually simplify this a little bit. I'm going to keep the logarithm the way it is, and I'm going to factor the numerator. That's x plus 3 times x minus 3 all over x plus 3, and it still equals 3. And now look, I get some nice canceling going on. The x plus 3's go away. Right? And what's left? The log base 4 of x minus 3 equals 3. We're going to do our conversion to an exponential equation. 4 to the third equals x minus 3. 4 to the third is 64. So x minus 3 equals 64. X equals 67. And that is a good answer. Right? If we jump back up here, if I put 67 in here, 67 plus 3 is 70. That's positive. If I come over here, 67 squared minus 9. Okay, I don't know what 67 squared is off the top of my head, but what I do know is that it's a whole lot bigger than 9. Right? Which means that when I subtract 9 from it, the result is still positive. And that's really the point that I care about. Right, so x equals 67 is a valid answer here. Now, what if you didn't see that? What if you didn't see that that factoring and canceling step? You still would have been fine. You still would have been okay. You would have made the switch here. X squared minus 9 over x plus 3 equals 4 to the third. And now you have a polynomial equation, which is okay. Right? 4 to the third is I just did that over here. Sorry, 4 to the third is 64. So this is x squared minus 9 equals 64 times x plus 3. And now you have a polynomial equation, right? Quadratic equation, which you can solve. You should be able to solve by factoring because you have to come up. We know that one of the answers is an integer, right? So you should be able to solve that by factoring, right? Either way works just fine. If you see the cancellation over there, obviously it saves you some work to having to deal with that quadratic equation, but you'll get to the right place either way. All right, so how about this one? Right, very similar, only now we're adding the two logarithms. So now I'm going to use the formula that says when I'm adding two logarithms, I can combine them together and multiply. All right, so let's do that. This becomes the log base 2 of x minus 2 times x minus 3 equals 1. And good. Now I'm going to go to the exponential version. 2 to the first equals x minus 2 times x minus 3. And again, we've got a polynomial equation. It'll be quadratic in a minute here. And the only way to handle this is to multiply it out, set it equal to 0, go forward from there. So I multiply out that right-hand side. Well, 2 to the first is just 2. The right-hand side becomes x squared minus 5x plus 6. And let's set it equal to 0, subtract 2 for both sides. X squared minus 5x plus 4 equals 0. And now I can factor it. This is x minus 4 times x minus 1 equals 0. And we get two answers. This factor gives me x equals 4, and this factor gives me x equals 1. All right. Now we gotta check these, right? If I do x equals 4, I get log base 2 of 4 minus 2 plus the log base 2 of 4 minus 3 equals 1. Okay, log base 2, well, let me write it out. Log base 2 of 2 plus the log base 2 of 0. Log base 2 of 0, 4 minus 3, sorry, I was looking ahead. 4 minus 3 is 1, and the log base 2 of 1 is 0, right? I skipped a part. And the log base 2 of 2 is 1. Yes, that does equal 1. Good. X equals 4 checks. How about x equals 1? Well, if I put that in there, I get log base 2 of 1 minus 2, and I'm actually going to stop right there. There's no need to go any further. 1 minus 2 is negative 1. And I know I can't take the logarithm of a negative number. So this is exactly the case I was warning you about. Right, this is how it's going to look when you get, and there's a name for it, right? When you get what's called an extraneous solution. So I have to throw this answer out. And my only solution here is x equals 4. All right, so that's how we solve logarithmic equations. All right, so in the next lecture in this series, we're going to turn around and see how we can go about solving exponential equations.